Hello and welcome back to SCI Teach. This is a practical lesson on the titration between tetrahydrosulfate 6 acid and sodium trioxocarbonate 4. So first of all, tetrahydrosulfate 6 acid is a strong acid. We're titrating against a weak base, sodium trioxocarbonate 4. So we're going to use methyl orange indicator for this titration. Now, I want to set up a question so that we go along with this question and carry out the practical. So the question is going to be the exam format, and then we carry out the instructions of the question from beginning to the end. Okay, so let's go. A is a solution of tetrahydrosulfate 6 acid. B contains 6 grams of sodium trioxocarbonate 4 in 1 dm cube of solution. We are to put A into a burette and titrate it against 20 or 25 cm cube portion of B. That's if you have 20 cm cube pipette, then that's 20 cm cube of B. If you have 25 cm cube pipette, then that's 25 cm cube portion of B, using methyl orange as indicator. And then we are asked to repeat the exercise to obtain consistent titers. We're going to, in this practical, do a rough and then 2 more titers to obtain consistent titers. Then we tabulate our readings and calculate the average volume of A used. Remember, A is the acid according to our question today, and B is the base. A is tetrahydrosulfate 6 acid. B for today is anhydrous sodium trioxocarbonate 4. All right, so the equation for the reaction is Na2CO3 plus H2SO4 yields Na2SO4 plus H2O plus CO2. All right, so we're going to start the experiment and then get to the point where we find the average after finding the 3 Titer values, and find the average, and then we get to calculations. What we're going to do in the calculations is to find the concentration of B in mole dm cube, find the concentration of A in mole dm cube, find the concentration of A in gram dm cube, find the volume of gas evolved in the reaction at STP, and possibly we calculate the number of hydroxonium ions that could be present in the solution. So the first part is to carry out the experiment and calculate the average titer. So let's go. So here is the practical. We see that A is tetrahydrosulfate 6 H2SO4. That's what is given to us in the question. So we put A in a beaker and label it A. And then we are told that B, okay, so B contains 6 grams of sodium trioxocarbonate 4. So we dissolve 6 grams of sodium trioxocarbonate 4 and then make a solution. Okay, so 6 grams of Na2CO3, make a solution, and then we pour a little in the beaker, which we're going to use for the titration, and label it B. Now we're going to turn put A in the burette. A is the tetrahydrosulfate 6 acid, so we put it in the burette, and remember your burette should be clamped already, and then remember you rinse the burette with what is going to be inside the burette. For now the acid is in the burette, so we rinse the burette with this acid and then we fill it up. Okay, so if it passes, you have to adjust the reading to sit on the meniscus. So you clearly see, bring it closer, clearly see that it's sitting on the meniscus. So you're sure that you are not adding too much or too less, or a little less. All right, so we measure 25 cm cube of B using the pipette. Our pipette here is 25 cm cube, so we measure 25 cm cube of B, which is the sodium triiosocarbonate, and pour it into a conical flask. All right, remember the question says we should use methyl orange, so we add just 2 drops of methyl orange to help us know when the titration process is complete. All right, okay, so we're ready to start the process. Remember that the white tile is there to make sure you see clearly the color change. All right, so let's go. So we start adding the acid, the tetraoxosulfate 6 acid, into the triiosocarbonate. You see that when the acid drops, the color changes to pink, so we are sure that the acid has a good consistency. Then we continue the process. So we swirl appropriately, so we make sure that the drops of the acid mixes up completely with the whole solution of Na2CO3. Okay, so we're going to keep titrating until we reach the end point where we see the color change, and that's about now. All right, so we've reached the end point, and then you see the color is no more orange or that light yellow color we saw. So we're done with the first process, which we could call this the rough. Okay, now let's see how much volume of the volume of A used. That's just on the 7 cm mark. That's 7. So we've used 7, and we started at 0.00. We measured and made the acid sit on the meniscus. So the endpoint was 7, so that means volume of acid used for our rough is 7. Now we're going to carry out the practical 2 more times. So this is the second time we prepared another 25 cm cube of B into the beaker, just like we did the first time, and then we'll going to add the same process. We add 2 drops of methyl orange and continue the same process. So ensure that anything you're putting inside there does not roll or rub on the walls, because you want to be sure that whatever is coming out of the burette is inside the solution, not on the walls, because the ones on the walls may not roll inside it, and then will account for less value in the burette or in the conical flask, but more value in the burette. So we titrate one more time, and hoping that our consistency would be good enough. All right, so waiting for the end points. Remember to swirl well until you meet a color change, which is about now. All right, so swirl well to make sure that the color mixes up, so you're not deceived by a slight color change. You need a consistent color change. All right, so that is our endpoint for the first start after the rough, and we check the volume we've used, and wow, that's just about the same as the first. So this is 14, sits on the 14 mark, so which means we've used another 7 cm cube, so our consistency is okay. All right, so the initial for the first starter is the final for the rough, because we didn't we didn't remove any more of the burette content. So we've used another 7 cm cube of A. We're going to do it one last time to ensure consistent titers. So the same way we prepare 25 cm cube of B, the base, and into a conical flask, drop methyl orange into it, 2 drops, and continue the process again. All right, now remember you're going to tabulate your values. So it depends on the concentration of the acid and base that I have, The one you have may be different, so you may not be having 7 7 like this, but just do it the right way, follow the processes like right way, and then you're going to get values that are correct. So we titrate for the last time and hope that we're going to have what our consistency was before. And see, it's like we added too much or a little more than we should. Okay, let's see. We'll see how much we've used there. All right, the position where we should read the burettes or take the burette reading from is where the clamp is holding the burette. So we have to adjust the clamp so we can see the level of the acid. Okay, so it's out now. Now we can take the measurement and we see on 21. Wow. Okay, not 21, a little bit beyond, just a little out. So we call that 21.1. 21.1 because it just passes the 21 mark. So remember, our initial is 14.00. That's where we ended the other one, and our final now is 21.10. So that means we've used 7.10 this time. All right, so we've finished the practical. We've done it 3 times, 1 the rough and 2 other ones to obtain consistent value. So we're going to find our average titer by adding the volume of acid used for the first and second titer. That's 7.00 plus 7.10 and divide by 2. That's to say 14.10 divided by 2, which will give us 7.05 cm cube of A. Remember, we're using A, that's A is the acid, so 7.05 cm cube of A used. Alright, so that is it. So let's solve the question that follows. The question we are asked is number 1, to calculate the concentration of B in mole dm cube. Number 2, the concentration of A in mole dm cube. Number 3, the concentration of A in gram dm cube. Number 4, the volume of gas evolved in the reaction at STP, that's the CO2 gas. And then number 5, to calculate the number of hydroxonium ions that is present in the solution. Remember, the equation for the reaction is Na2CO3 plus H2SO4 yields Na2SO4 plus H2O plus CO2. Alright, so let's solve the first question. Number 1, concentration of B, and B is the sodium triisocarbonate 4. So concentration of sodium triisocarbonate 4 in mole dm cube. Now our B, that's Na2CO3, to find the molar mass is Na, 2 of them, no? Na is 23. So 23 times 2 is 46, and then C is 12, so plus 12, and then O is 16. 16 times 3 is 48, so plus 48. So 46 plus 12 plus 48, and we have 106 gram mole as the molar mass of B, which is Na2CO3. So concentration of B is in mole dm cube is like finding the number of moles. That's the amount of moles. So N equals to number of moles equals to mass all over molar mass. Amount equals to mass over molar mass. And the mass is 6 grams of B, as the question gives us, that was dissolved. And then the molar mass is 106 gram per mole. So that is mass over molar mass 6 all over 106, which is 0.0566 mole dm cube. And that is our concentration of Na2CO3 in mole dm cube, 0.0566. Now remember that the question said that B contains 6 grams of sodium triisocarbonate 4 in 1 dm cube of solution. So that's a standard solution already, my question. Imagine that in your own question, it's not a standard solution. Imagine that 6 grams or whatever grammage was dissolved in 250 cm cube of solution. If that's the case, your formula was not of mass over molar mass will end up being mass over molar mass times the volume of solution, the volume of water used. That's the 250 cm cube, but you convert the 250 cm cube to dm cube, so 250 will be 0.25. All right, so that would be 6 all over 106 if it's 6 times 0.25 if the volume was not a standard solution, like if it wasn't 1 dm cube. But our own here is 1 dm cube of solution, so we go straight up and say 6 over 106 because we would have sent times 1 dm cube. So 106 times 1 is the same as 106, so just leave it at 6 all over 106, which gives us 0.0566 mole dm cube, which is our concentration of B, Na2CO3 in mole dm cube. So question 2 says we should find the concentration of A, which is the acid, the tetraoxosulfate 6 acid, in mole dm cube too. Now we're going to use the formula CaVa all over CbVb equals to Na all over Nb, and we'll make Ca subject because the concentration of A is Ca. Subject of equation, that would be Ca equals to CbVb Na all over VaNb. And our Cb is 0.0566, concentration of base that we just found in question 1. Our Vb is the volume of base, volume of sodium triiosocarbonate 4, which was 25 cm cube. Remember that we measured using the pipette. So Vb is 25, and Na, we have to look at the equation again. That is Na2CO3 plus H2SO4 yields Na2SO4 plus H2O plus CO2, and we see that in this balanced equation, the number of moles of Na2CO3, that's the B, to the A, which is H2SO4, is 1:1. So number of mole of acid is 1, number of mole of base is 1 also. So that's to say that our Na is 1 and our Nb is also 1. So Cb 0.0566, Vb 25, sorry, Na equals to 1. So we multiply all those all over Va, volume of acid that we had from our average titer after titrating and creating our table of values, which gave us 7.05. So Va equals 7.05 times Nb, which is equals to 1. So we multiply all those and substitute, and then we have that concentration of acid in mole dm cube is 0.201 mole dm cube to 3 significant figures. Right? So you discover that a balanced equation is very useful in finding the concentration of acid or concentration of base if you're using this formula. Alright, so we move to the third question, concentration of A in gram dm cube. Now remember, A is H2SO4. So when we're dealing with gram dm cube, we need to find molar mass too. Molar mass of H2SO4 is H is 1, but there are 2 of H, so 2 plus S is 32, so plus 32 plus O is 4 and O is 16, so 16 times 4 we have 64. So 2 plus 32 plus 64, we have that the molar mass of H2SO4, that's our A, is 98 gram per mole. So then we find the concentration of this A in gram dm cube by saying gram dm cube equals to mole dm cube times molar mass. And the mole dm cube is what we just found in question 2, that's 0.201. So we say gram dm cube equals to 0.201 times the molar mass we just found, which is 98 gram per mole. If we multiply that, we have that our concentration of A in gram dm cube is 19.698 gram per dm cube. Now the next question, question 4, says that we should find the volume of gas evolved in the reaction at STP. The gas here is carbon dioxide, and from the equation we can see that 1 mole of Na2CO3 yields 1 mole of CO2 on the other hand. So that means Na2CO3 1 mole of Na2CO3 equals to 1 mole of CO2 at STP. So that means number of mole of CO2 is equal to the number of mole of Na2CO3. And the number of mole of Na2CO3 we found, that's B. The number of mole of B was Na2CO3. Number of mole of Na2CO3 we found in question 1 was 0.0566. And from this solution we just solving, we've discovered that number of mole of Na2CO3 is equal to number of mole of CO2. And since the number of mole of Na2CO3 is 0.0566, then the number of mole of CO2 is same, which is 0.0566 mole. Now we then find the volume of CO2. Remember that molar volume is 22.4 dm cube. So if we have number of moles, then we multiply that by molar volume. So number of moles and molar volume, which is 0.0566 times the molar volume, which is 22.4 dm cube, will give us 1.27 dm cube at STP. But take note that we in the question we used, or in our titration, we used just 25 cm cube of the Na2CO3. And mind you, before I forget that, while we are making use of Na2CO3 when we are looking for volume of gas evolved, is because the CO2 was only evolved from Na2CO3. So Na2CO3, the base, was the part that CO2 evolved from. So we have to use that. But now the Na2CO3 we used in this question, in the titration, was 25 cm cube. But the answer we just have for volume of CO2 used is 1.27 dm cube. Dm cube is 1000 cm cube, but we just used 25 cm cube. So we have to calculate the volume of gas evolved from just 25 cm cube. So that would be 25 over 1000. We convert the 25 to dm cube. 25 over 1000 times the 1.27 dm cube we just solved, and we have that the volume of CO2 liberated in 25 cm cube is 0.0318 dm cube, or we said 31.80 cm cube if we want to use cm cube at STP. And then lastly, we are to calculate the number of hydroxonium ions that could be present in the solution. Remember that hydroxonium ion is H3O plus, and it is formed when an acid enters into water. You know, water, we have H2, 2H, okay, H2O, sorry, yes, 2H, but H2O. So an acid has hydrogen ions in it. So if an acid enters into water, it tend to give an extra hydrogen ion to water. So if water accepts that hydrogen ion, then H2O will become H3O, and H2O was already neutral. If another H comes in, then it's going to become an ion because there's an extra one positive charge coming in. So H3O is formed. That's hydroxonium ion, which is an ion actually. So we deal with the acid that entered into water to form hydroxonium ion. So we write an equation to represent that. That's to say H2SO4, which is the acid we used now in this question, plus water, so it entered into water and yields the hydroxonium ion plus SO4 2 minus sulfide ions. Now if we balance the equation, we discover that now H2SO4 yielded 2 moles of hydroxonium ion. So 1 mole of H2SO4 produced 2 moles of H3O plus, that's hydroxonium ion. That is to say that, you know, we found concentration of A, that's the H2SO4, in mole dm cube, and that was 0.201. That's our 1 mole now. So So 1 mole of H2SO4 is 0.201 mole of H2SO4. You understand what I'm saying? So we replace that and say 0.201 mole of H2SO4 produce 2 moles of hydronium ion, and then we're looking at the relationship. If we do number of moles of H2SO4 that's in comparison with hydronium ion, so we have 1:2. So if H2SO4 is 1, that's 0.201, and then hydronium ion is 2, that would be 2 times 0.201. So that will give us that hydronium ion, the number of moles is 0.402. But we remember that 1 mole of any substance equals to 6.02 times 10 raised to power 23 particles. Now the particles we are dealing with now is ions, not atom, not molecules. So it's ions we are dealing with now. So 1 mole of hydronium ion would contain 6.02 times 10 raised to power 23 ions. Remember Avogadro law or constant. So that would mean that 0.402 moles of these hydronium ions will contain 6.02 times 10 raised to power 23 times 0.402, which will give us that there are 2.42 times 10 raised to power 23 ions, that's hydronium ions, that could be present in that solution. Okay, so we have calculated the number of hydronium ions that could be present in the solution, 2.42 times 10 raised to power 23. So you see, the calculations are as straightforward as possible. We just need to understand the principle involved and the correct calculation equation or formula and the methodology. And then if we do that, we can solve this and come out with flying colors. Take note, if you carry out the practical itself accurately, you've already gained about 10 to 12 marks. And then if you do all these calculations, supposing you have all these calculations come out and you do all the calculations you're required to do completely and accurately, you come out with about 12 marks also. So you could be playing around 20 to 24 marks if you don't take this seriously. But if you take this seriously, you may be having your 20 to 24 marks as a bonus just for answering question 1. So I advise you to take this seriously, go over it again and again, understand, and if you have a question, drop it on the comment section and I will explain further. Remember to subscribe to this channel so that you will be able to get access to other enriching contents when they are available. Thank you.